Quickly Quantum. China just built the bureaucratic machinery to write its own quantum rulebook, the same playbook that gave it outsized influence over global 5G standards. And on the other side of the board, a new analysis argues Western export controls have quietly stopped being about keeping secrets and started being about picking winners. Same week, same fight over who gets to define the next computing paradigm. So today we're running both of those as co-leads, because neither one makes full sense without the other. Before that, in the headlines, D-Wave teams up with Nasdaq's Verafin to hunt financial crime. IBM and RIKEN claim they beat a supercomputer at a real materials physics problem. And Japan's OptQC and NTT go deeper on a fault-tolerant million-qubit optical machine. Welcome back to Quickly Quantum, your daily brief on the quantum frontier. It's Monday, August 3rd, 2026. Let's get into it. First up, D-Wave and Nasdaq Verafin. D-Wave, the annealing quantum computing company trading as QBTS, announced an agreement with Verafin, Nasdaq's financial crime detection unit, to explore quantum hybrid machine learning for catching fraud and money laundering. And the reach here is real. Nasdaq Verafin's technology is already used by more than 2,800 financial institutions, representing $13 trillion in collective assets. The plan starts small, with a proof of concept where Verafin uses D-Wave's annealing hardware, quantum computers built to solve optimization problems by settling into low-energy states, to analyze hundreds of data signals across account activity, transaction patterns, and counterparty networks, hunting for unusual behavior conventional systems miss. D-Wave CEO Dr. Alan Baratz called it, quote, an important opportunity to explore quantum computing's potential in addressing some of the financial services sector's most complex problems, end quote. Here's the asterisk, though. Independent reporting notes this deal is in early pilot stages, with no public performance benchmarks yet. A statement of intent, not proof that quantum beats classical here. It also lands right after D-Wave's AT&T Telecom deal last week, and just ahead of D-Wave's second quarter earnings, a pattern worth clocking. Now here's one that could matter more than the press release framing suggests. Blue Qubit, IBM, Kurma, and Japan's RIKEN say they've pulled off a quantum advantage, beating the best classical methods, not on a contrived benchmark, but on a real materials physics problem. The task was modeling a Floquet Ising magnet, a material whose subatomic oscillations matter for things like room temperature superconductors and better batteries. RIKEN threw more than 500,000 CPU core hours at Japan's Fugaku supercomputer trying to nail it down, while Blue Qubit ran state-of-the-art tensor network and polypath simulations, the leading classical tricks for approximating quantum systems across GPU clusters. Both hit a wall. The classical methods couldn't converge at larger scales. Then, Qubidema's error mitigation software, QESEM, ran the same problem on IBM's 156-qubit Heron processor, and, checked independently against a trapped ion machine from Quantinuum, landed percent-level accuracy without needing full error correction. Blue Qubit co-founder and CTO Heike Tepanyan put it this way, quote, proving true quantum advantage requires rigorous verification against the uppermost limits of classical computing, end quote. This is exactly the kind of practical result IBM's quantum bet has been chasing. But it's worth flagging this is a joint release from the vendors making the claim, not independent peer review, and quantum advantage claims in this exact space have a track record of getting picked apart once outside researchers get their hands on the data. Over in Japan, OptQC and NTT are deepening a partnership that's been running since November of last year. NTT, the telecom giant, is putting fresh capital into OptQC, a photonic quantum computing startup, as the two chase a fault-tolerant million-qubit class optical quantum computer, one built with particles of light instead of, say, superconducting circuits. The appeal of optical quantum computing is that it plays naturally with existing fiber optic networks and, in theory, scales more efficiently. The new agreement covers joint research, supply chains, and use cases in finance, manufacturing, and drug discovery. OptQC already runs its first machine, called Mokurin, at a national research center in Japan, and the two companies say a joint team recently built what they're calling the world's highest quality quantum light source, a key building block for any optical machine. I'll say the same thing about this one I'd say about any press release. It's thin on the numbers that would let us actually grade it. No qubit counts, no fidelities, no timeline. So file it as a strategic bet, not a technical milestone, until harder numbers show up. Our first lead today, and here's its thesis. Whoever writes Quantum's rulebook may end up owning the industry built on top of it, whether or not they build the best hardware. Here's what happened. On July 30th, at a meeting in Beijing, China's Ministry of Industry and Information Technology, MIIT, the ministry overseeing the country's tech industry, formally stood up a new national technical committee dedicated to quantum information standards. Its job is to write and revise the industry standards covering foundational quantum information technologies, quantum computing, quantum communication, and quantum precision measurement. Essentially, the rule book for how quantum hardware, software, and networks get built, tested, and certified inside China. Now, on its own, a government committee sounds like the most boring possible story in quantum computing. It doesn't change a single qubit, doesn't run a single algorithm. And that's exactly the trap, because the detail that actually matters isn't the committee. It's where its secretariat lives, the China Academy of Information and Communications Technology, or CAICT, a MIIT-affiliated think tank. CAICT is the same institution that ran China's push into 5G standards. And in 5G, CAICT wasn't just writing memos. It ran the technical trials that certified equipment against domestic Chinese standards. And those domestic standards became the baseline China brought to the table at 3GPP and the ITU, the international bodies that actually set global telecom standards. That's the difference between setting your own rules at home and shaping the rules everyone else eventually has to follow. So the question the analysts are actually circling is whether CAICT can run that exact playbook again, this time for quantum. And China's laid real institutional groundwork to try. The country has named quantum technology one of the strategic industries it's cultivated in 2026, right alongside future energy, embodied AI, brain-computer interfaces, and sixth-generation wireless. MIIT has said outright it wants to promote quantum breakthroughs, grow leading domestic quantum companies, and, in its own words, participate actively in the formulation of international standards and rules. This committee is the vehicle for that last part. It's also not happening in a vacuum. This is the same year China's Origin Pilot quantum operating system went public for free download back in February, lowering the barrier for anyone in the country to start writing quantum software. And in May, Chinese researchers unveiled Zhujiang 4.0, a programmable photonic quantum computing prototype they say set a world record in optical quantum information technology. Put those together with a standards body, and you get a pretty coherent strategy. Build the machines, build the software layer, and now build the rulebook that says how all of it should work, all under one coordinated push. CGTN, the state broadcaster reporting on the announcement, quoted the committee's formation as, quote, marking an important step toward leveraging the foundational, strategic, and guiding role of standards, promoting the high-quality development of the quantum industry, and strengthening international cooperation in the field, end quote. The kind of sentence that reads like nothing until you remember it's describing the same institutional move that helped decide who profits off every 5G base station on Earth. Here's the honest caveat, and it matters. Standing up a committee is an institutional signal, not a technical one. It doesn't change any hardware or algorithmic reality today, and whether this translates into actual leverage over global quantum standards bodies, the way CAICT's 5G work did, is going to take years to show up. There's a real chance it doesn't, because quantum computing's underlying physics is nowhere near as standardized as telecom radio protocols were even in early 5G. Superconducting, trapped ion, photonic, and neutral atom qubits don't talk to each other the way cell towers do, so there may just be less room for one country's standards to become the default. But the instinct behind it, get organized institutionally before the technology matures, not after, is exactly the instinct Western governments have historically moved slower on, which is basically the mirror image of the story we're covering next. Our second lead, and it's got its own thesis, call it the anticipatory containment story, the idea that the West has quietly stopped treating export controls as a lock on the door and started treating them as the blueprint for who wins the whole building. A new analysis from the International Institute for Strategic Studies, IISS, a UK-based defense and security think tank, argues that Western governments, led by the US, have fundamentally changed how they use export controls on quantum technology. The old model waits for an industry to mature commercially, then slowly restricts finished products and works backward up the supply chain. IISS says quantum is being regulated the opposite way. Nearly every layer of the technology stack, hardware, cryogenics, materials, manufacturing tools, software, even the technical know-how, is getting restricted before the industry has any large commercial market at all. IISS researchers Dongyun Cho and Dr. Maria Shigina give this a name: anticipatory containment, an effort to slow down strategic rivals before quantum technology gets widely commercialized, while still trying to preserve enough international scientific collaboration to sustain innovation among allies. Their framing of the stakes, in their own words, quote, "The decisive question is no longer which technologies to deny an adversary, but which nodes of one's own ecosystem to sustain," end quote. The mechanism IISS zeroes in on is what it calls critical nodes, a small number of choke points where a handful of companies, almost all in allied countries, control something nobody can easily substitute. Isotopically enriched silicon-28, used in silicon spin qubits. Helium-3, needed for the dilution refrigerators that cool most quantum computers down near absolute zero, and which stays scarce because it's mostly a byproduct of tritium decay. Electronic-grade synthetic diamond for quantum sensing and memory. On the equipment side, precision cryogenics and specialized photonics that IISS says are genuinely hard to swap out without a real performance hit. This builds on a regime already in place. The U.S. Commerce Department's Bureau of Industry and Security has worldwide export controls covering quantum computers and the equipment, components, materials, software, and technology that go into them, alongside restrictions on gate-all-around transistor technology, which underpins high-performance computing chips more broadly. There's real history behind why this shifted. The report traces it to the Wassenaar Arrangement, the old multilateral regime for controlling dual-use exports, essentially breaking down after Russia blocked updates to it following 2022. Since 2024, the US, the EU, the UK, Japan, and other allies have been building their own largely harmonized but legally separate national systems instead, outside that old multilateral framework. IISS's own account on X put the bottom line plainly. At IISS_bytes wrote, quote, "The US and its allies have built aligned export controls on quantum technology, targeting supply chain choke points before the industry matures. Their success will depend not only on denying rivals access, but also on sustaining the allied ecosystem," end quote. Other quantum community voices are making the same argument from the talent side rather than the hardware side. At NetCreate, a quantum computing and security analyst warned on X, in a summary of a longer thread, that China has successfully attracted many researchers trained at leading US and European institutions, and argued that without faster, more coordinated Western action, today's narrowing technology gap could become tomorrow's reversal. At Hannah Suds, who focuses on the quantum sector on X, made a related case, arguing China's approach has been to actively recruit Western-trained researchers back into a coordinated national infrastructure. And in her read, the IonQ Skywater tie-up is the West's answer to exactly that recruitment strategy. I'll flag that last part as her own interpretation of the deal's significance, not something this show has independently verified. Here's the honest tension IISS doesn't fully resolve, and it's the same one critics have raised since the US first started expanding dual-use restrictions. Chokepoint controls only work if you don't also choke off the academic collaboration and talent pipelines that keep the allied side innovating in the first place. Cut off the wrong pipeline, and you've handed your rival the very researchers you were trying to keep an edge over. So put these two leads side by side, and here's what the pairing actually reveals. China is building institutional machinery, a standards committee modeled on the exact playbook that gave it outsized influence over 5G. While the West is building institutional machinery too, just aimed at the supply chain instead of the rulebook. China's move is about writing the definitions everyone eventually has to use. The West's move is about controlling the physical choke points, the helium-3, the dilution refrigerators, the enriched silicon, that any definition eventually has to run on. Neither side is actually betting on having the best qubits. Both are betting on owning the scaffolding around the qubits. And that's the tell. This fight over quantum leadership is increasingly happening in ministries and export control offices, not in labs. Hype check time. I'm giving this pairing a 4 out of 10 on substance. Here's why. Both moves are real and corroborated, with serious institutions behind them, not vaporware. But neither one has produced a single new qubit, algorithm, or dollar of commercial revenue yet. This is entirely a bet on positioning 5 years out, and 5 years is plenty of time for either playbook to get overtaken by events. So next time a quantum headline crosses your feed, a new committee, a new export rule, a new capital tie-up, ask yourself which piece of the scaffolding it's actually claiming, the chip, the choke point, or the rulebook, because that's the real scoreboard now, not the qubit count. If you want that lens applied to tomorrow's headlines too, follow Quickly Quantum wherever you're listening. And if today's episode helped you make sense of the geopolitics, send it to someone who keeps asking you what quantum computing even is. This has been Quickly Quantum, an AI-voiced podcast created and built by a real human using today's cutting-edge technology. Nothing you heard on this show is financial advice. I'm Brian Lampert, and I'll catch you all tomorrow. Take care.